Hello and welcome back. Next we'll talk about timing for flip-flop based designs. Of course, as described in the class mantra, flip-flops will be the main type of storage element you'll be using in the rest of this class. And the timing equations we're about to go through will also be implemented in the synthesis tools, and you'll have to understand intimately how that is done. But first, all we're going to do is talk about deriving the timing equations for setup and hold conditions for flip-flop based designs. To do that, we first will have to define setup and hold, and in fact all the major timings are related to edge-triggered flip-flops. Of course, the behavior of an edge-triggered flip-flop is the output Q becomes equal to D after the clock edge. However, there's some details in the timing that are very important in order to get working designs. There is a period of time around the clock edge in which D is not allowed to change. If D changes during this time, it can lead to what's called a timing violation. The time before the clock edge is referred to as the setup time. The period after the clock edge, during which D cannot change, is called the hold time. In the next two slides, we'll actually explain what could happen if D changes during this time. In addition, there's actually, of course, a real delay between the clock edge changing and Q become equal to D. This is referred to as the T clock to Q delay. On the bottom left, we have an example of a two-stage logic, which we'll be using in a few moments to derive equations. In that two-stage logic, I refer to both clock and clock bar, and I do want to remind you in general that even though the clocks are designed to try to arrive at the same time, in practice there is a skew, and we do not know in advance which direction the skew is. The tools cannot guarantee that. So the skew is bounded, but we don't know whether it's positive or negative at a particular point in reference to another point, because the skew is caused by random variations. So a couple of slides first on what happens if we have a timing violation. That is, if D actually does change during the setup and hold time. Well, first of all, I'll remind you what happens if D changes sufficiently in advance of the clock edge for there not to be a setup or hold violation. And what happens is Q changes T clock to Q after the rising edge of the clock, and this T clock to Q that's specified in the timing parameters for the flip-flop will be accurate. So let's look at some of the things that can happen if D changes after the setup point here. Well, if D changes early after the setup point, the most likely event is that Q will still change and change correctly, as on the bottom left, but it will take too long to change. That is, the flip-flop will operate slower than is specified, and particularly slower than the timing tools have been assuming. So you'll get incorrect timing in the next logic stage, leading to a problem there. And in fact, the chip would fail. On the right-hand side, we look at the situation where D is changing quite late during the setup and hold period. What could happen here is that Q might not change correctly at all. You might see a small bump, you might not see any change at all. And thus, Q will be incorrect in the next clock cycle, leading to a logic failure in the design. If you're running Windows, it will be the blue screen of death. Another possibility, if D changes during the hold period, is that the flip-flop operates correctly, but now look at what's happened. The change in D is leading to a race through in the flip-flop, and we'll see this in a moment when we look at hold violations. So in general, we're going to look at two stages of logic to derive our timing equations. Two registers talking to each other. Left-hand register is input D1, output Q1. The right-hand register input D2 and output Q2. There's a logic delay, And I'm going to consider here both the minimum fastest logic delay on the shortest logic path when I consider hold violations. And for setup violations, I'm going to consider the longest logic delay on the longest logic path. I'm going to give the clocks at the two registers different names to account for the skew. You can call the clock 2 clock dash. And remind you that we cannot predict in advance which direction the skew will be, whether it will be positive or negative. So let's look at setup violations first. And just for reference, I put the previous figure, figure on the previous page in the top right corner. So, first of all, which is the worst case for the skew of clock to clock dash? The worst case is if clock dash is advanced, that is, arrives earlier than clock. Then we only get from this point here, the rising edge of clock, to the next rising edge of clock dash for all the logic to propagate through. And this is shorter than in the opposite case if clock dash was arriving later. So let's look at there's an equation on this page here, and this equation specifies the safe condition for the relationships between the period of the clock, T clock, and the delay parameters that we'll be interested in. Notice it's greater than or equal to. In fact, in the critical path of the design, the tools will make it so that it's equal to. Let's derive this equation pictorially. After the rising edge of the clock, on register 1, T clock to Q later, Q1 of that register changes. Then we're looking at the worst case logic delay, which is the longest logic path under the slowest parametric temperature and voltage conditions. Particularly, as you're most probably aware, CMOS operates slower at higher temperatures, and obviously it also operates slower at lower voltages. In addition to that, there's the process variation in the factory, and we have to use the statistically worst case process variation in the factory to work out T logic max. So D2 arrives at this time here. It has to arrive at least a setup time before clock dash rises. And I remind you that the worst case scenario is when clock dash is retarded with respect to clock by T skew. So, has the example I've drawn here actually satisfy the setup equation I set up at the top? Actually, yes, it does. T clock is greater than the sum of these four parameters drawn in this example. And in fact, that difference is referred to as the timing slack. That is the excess amount of timing that was available in the clock period that we haven't actually used. And you see this term referred to in the synthesis tools. And I remind you that the key to the setup time is that T logic, that is D2, must change before this time here in order to prevent what's called a setup violation. Next, look at hold violations. And you can see the constraint equation to prevent hold violations at the top of the page. Notice something here. Is the clock period in this equation? No, it's not. It's simply an equation related to conditions that can happen around the edge of a clock. You can see the equation is that the sum of T hold plus T skew must be less than T clock to Q min, that is, under the fastest process, the highest voltage and the lowest temperature, plus T logic min, that is the shortest logic path operating under those same fastest conditions. Let's pictorially derive the scenarios with and without hold violations. First one we'll do is with a hold violation. So the hold violation, of course, occurs if D2 changes during the hold period after clock dash rises. So again, which is the worst case? The clock dash is arriving after clock or clock dash is arriving before clock? The worst case is when clock dash is arriving after clock, because that gives more time for D2 to change after the original clock. So this is the left-hand side, that is, D2 must change after this point here in order to prevent a hold violation. Let's look at the right-hand side. T clock to Q min is how soon after clock Q1 changes under the fastest possible conditions. T logic min is the shortest logic path under the fastest conditions leading to a change in D2. Does the example drawn here satisfy the equation above? No, it does not. We have an incorrect operation. This could lead, for example, to either just Q2 being incorrect, that is, it does not change properly, or, just as bad, Q2 changing around the same clock edge as Q1. That is a race-through condition. We'll see what happens in the correct situation on the next slide. What we want to see is Q2 changing over here in the next clock period, because it should take one clock period to get through this particular register-to-register stage, as it does for all other register-to-register stages in your design. So here we have a hold violation. Okay, let's look to see a situation where we don't have a hold violation. In this example, T clock to Q min and T logic min are faster. Thus D2 is changing after the end of the hold time as delayed by the skew in the worst direction. And Q2 won't actually change until the next clock period, as it should in any two stages of logic. So this situation, the constraint at the top of the page is satisfied and we do not have a hold violation. So that brings us to the end of this submodule. I remind you of the main points here. In a D flip-flop, the input D cannot change during the setup hold period around the edge. Setup violations are the situation where the clock period is too slow in comparison with the longest critical path under the slowest conditions, leading to the signal arriving during the setup time or later. Hold violations occur under the fastest conditions, which lead to the signals arriving too early in the clock period, causing incorrect operation or a race through. And I remind you again that skew is random. The worst case skew condition is positive or negative depending on the particular situation we're looking at. What I'd like you to do now is do the internal quiz before proceeding to the next submodule. Thank you.